And if I have time, we'll discuss GHC state and the Hardy state. Right. Okay, so the CH-SH inequality is sort of a outcome or a sort of a equivalent in some ways to the Bell inequalities, which I'm sure you've all heard about. Okay, so of course it has a long and famous history. In 1926, Einstein wrote to Max Born, Born's rule for probability. He wrote to him and said, "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but it does not really bring us closer to the secret of the old one." I think old one is Einstein's way of saying God, right? "I, at any rate, am convinced that he," again referring to God, "does not throw dice." So this is the famous sentence from Einstein that he doesn't believe in quantum mechanics because it seems like God is just throwing dice and getting random outcomes. And to further enhance his reason for feeling uncomfortable with the theory, in 1935, they introduced the EPR pair, that is Einstein, Podolsky, Rosen. Which is the famous state, which is also called the Bell state. I've already introduced to you this Bell state in earlier lectures. Okay? So the two parties, A and B, Alice and Bob, which are representing the left and the right qubits, they are just given the state, prepared by somebody else, Charlie, for example. Okay? And actually I should mention that in the actual original paper for EPR, they use not 0 and 1, because 0 and 1 you can think of as spins or photon polarization or qubit states like we've discussed. They were using position and momentum basis instead. So it was a much more sort of complicated notation that they had to use to keep track of position and momentum being continuous variables. So they did it with that variable basis, but the general argument was still the same. Okay, and of course our result here, this state here is of course famous because it gives us this weird effect that if Alice measures 0, then Bob will by definition measure 1, and if Alice measures 1, then Bob will by definition measure 0. And I already proved to you in the very beginning, not very beginning, but when I started talking about quantum information, I proved to you this is true even if I measure in any other basis. If A and B measure in some other basis, which of course should be an orthogonal basis for complete, orthonormal basis for completeness, let's call it B and B perpendicular as the new basis, and even if they measure in this basis, they will also obtain the same correlations. Okay. Further, this is true even if Alice and Bob are separated by very big distances. Like maybe one is in Pluto and the other is on Earth, or one is in this on this planet and the other person is across the galaxy, etc. This should all still be true according to these. So this seems to contradict sort of localism. So Einstein was very upset about that. So he was trying to create effectively what nowadays we would call local hidden variable theories, meaning there is some additional information inside each qubit's wave function or some additional variables which are hidden to us, which we don't directly measure, which govern the behavior of the wave function, especially upon measurement. It causes the wave function to behave in a certain way. Okay? And in 1964, this is sort of a history, I guess, also of the whole field. 1964, Bell proposed an experiment. Okay? To rule out hidden variable theories. Which is basically what I'm trying to say is that Einstein said, oh, the wave function is not a complete description of the state of the system. There are these other hidden variables which impose conditions upon measurement and also will rule out these kind of non-local correlations between two people who are separated by large distances. So he proposed experiments that will rule out not just Einstein's favorite local hidden variable model, but any local hidden variable theory or model. Okay? And how can you do that? Right? You may ask, wait a minute, like how do you rule out every possible local hidden variable theory? The idea is that for every possible experiment, you let the particles agree prior to any of the measurements. Let's say the particles interact, right? They create some hidden list of all the outcomes of every possible experiment that they could be ever subjected to. Imagine that the particles of these hidden variables, really, these hidden variables or God, whatever you want to call it, was in there and it knew every possible experiment that it was going to ever be applied onto it. Okay? So prior to the particles, and this is what local hidden variables mean, right? I mean, they have to be local, they have to be happening when the particles have been interacting with each other or local to each other. And at that time, they've already decided secretly, they have a list somewhere, stored in some hidden variables, which tell them the result of every possible experiment that could ever be applied to those particles, right? That's the only way we can sort of assume that we can rule out every possible hidden variable theory, okay? So that is the idea. And then what we are going to say is, we can separate the particles, okay? Then they can no longer communicate with each other. Okay, so they no longer can communicate after they have traveled across a galaxy or on another planet, whatever it is. They no longer can communicate after that initial interaction, but they have that list. They have that hidden variables stored somewhere. Okay, some kind of memory in their hidden variables, which will tell them, oh, this particular measurement was carried out on me. I need to give this particular result to the experimenters. Okay, so that's the secret of the hidden variables, right? They are secret, we don't know them, but they have the secret property that if I apply a particular experiment, they'll give me a particular result. Okay? Okay, so that's the, I won't write all that here, but I'll just say particles interact locally and have a list of outcomes, and the list can be infinitely long. Okay? For each or any experiment. Okay? And after they separate, they cannot communicate. But can consult the list. So there are two ways now I can proceed. One is the way that is given in all the textbooks, which proves this so-called CH-SH inequality, which is just a form of the Bell inequalities. By the way, I should say CH-SH represents Clauser, Horn, Shimoni, Holt. And that is the name of the four scientists who produced this very, very famous paper and this famous inequality. So I have two ways sort of introducing the proof of this inequality. Okay, the first way is the classic way, So let me just briefly outline it, and I will, and then I have another way which I think is a more fun way. Okay, so, but first let me introduce the classic way. So this is the paper, the proof of that paper. Okay, and I'll explain what the proof is by just simply outlining what the, so Alice measures two properties. A1 with the result A1 equals plus minus 1. Okay? And you can think of these as, say, like, you know, Alice has some particle whose position she wants to measure. She shines a bit of light on it, okay? And she finds out that the particle is in, say, position 1 or position 2. And that result is encoded as either plus 1 or minus 1. Okay? And let's say she also measures another property, A2, with result A2 equals plus minus 1 as well. Okay? And this could be some other property associated with this, whatever she's doing, right? Maybe she's measuring now the color of this particle, okay? Or some other property, spin, you know, whatever you want to call it, and she assigns two outcomes. They are A2, which is similarly, there's B1 with B1 equals plus minus 1, and B2, this is for Bob. Okay, this is Alice, and this is Bob. Okay. And now we consider the following equality or following quantity, which I will label as S, okay, which is composed of this A1B1 plus A2B1 plus A2B2 minus A1B2. Okay? So this is the property that we are now looking at, or the quantity that we are looking at, which is formed by taking the outcomes of all of these results, of these experiments, and calculating this particular quantity, which you can easily see is just A1 plus A2 times B1 plus A2 minus A1 times B2. So we carry out this particular property, and since A1 and A2 is definitely either plus or minus 1, right? So either A1 plus A2 is equal to 0. So when either A1 is 1 and A2 is minus 1, or the other way, A1 plus A2 will be 0. Or both of them will be plus 1, in which case A1 plus A2 will be 2, or both of them will be minus 1, in which case A1 plus A2 will be minus 2, right? And similarly, you can show A1 minus A2. So this is one possible case, right? Which represents that when A1 plus A2 is 0, that means that either A1 must be 1 and A2 must be minus 1, which means A1 minus A2 must be plus 2, okay? Or the opposite, which means that it must be minus 2, okay? And of course, this OR comes with the, accordingly, this combination, A1 minus A2 is now 0, okay? So you can see the switch between these two values, plus minus 2 and 0, just depending on the values of A1 and A2. And we can also say that because B1 and B2 now are either plus 1 or minus 1, again, we must have, very straightforward now to verify that this quantity S, therefore, must be equal to plus or minus 2, right? Because either the situation is that A1 plus A2 is 0, okay, so this part drops out. Then you're left with A2 minus A1 times B2, and B2 again can only be plus or minus 1. So A2 minus A1, since it's either plus or minus 2 in this case, Therefore, the overall result is also plus or minus 2. And similarly, in the other situation, we will have the other term drops out. This part will be plus or minus 2 multiplied by b1, and therefore the answer must be always equal to plus or minus 2. Okay? So we have concluded that the quantity a1 b1 plus a2 b1 plus a2 b2 minus a2 b a1 b2 must, if a1 and a2 have these properties with these outcomes, remember going back to the hidden variable approach, this quantity s must always be plus or minus 2. Okay? This is the local hidden variable prediction. And now I will obviously going to show you that in quantum mechanics that the expectation of this quantity will always be lesser than or equal to this quantity 2. Okay? It's greater. Okay? So let P of A1, A2, B1, B2 represent the probability, which is the joint probability, that A1 equals A1, B1 equals A2 equals small a2, etc. Okay? Okay, now I just carry out some simple algebra. E of this quantity S, which is denoted over here, is just the sum over all possible values of A1, A2, B1, B2 of this joint probability distribution, A1, A2, B1, B2, times every available outcome in this combination, plus A2, B2 minus A1, B2. But we already said that this quantity, which is over here, which is the outcome of this results, must always be lesser than or equal to now this probability distribution times A1, A2, B1, B2, P of A1, A2, B1, B2. Okay, and times just this outcomes, which we have already concluded can only be plus or minus 2, and so this must be on plus or minus 2. Okay, we can replace that this quantity outcome must always be plus or minus 2. Okay. But the sum over all the joint probability distributions, we know that this expectation that the sum of all the joint probabilities must be 1. So the expectation value of S must be lesser than or equal to plus or minus 2. Okay. Now suppose we prepare, and of course this joint probability, we can also expand it out on the left hand side. E of S must be equal to the sum of all the individual expectation. So let's just write that out, plus E of A2 B1 plus E of A2 B2 minus E of A1. Okay, that's the left hand side, because that's just simply what S stands for. So that's the expectation value of this quantity when we consider it in this. Okay. So So now, so we have that the left-hand side, which is just the sum of all the expectation values, must be lesser than or equal to this plus or minus 2. And now, of course, I'm going to carry out the possibility that A and B have prepared an entangled state. So this is the classical prediction. Okay. Now psi, which is what A and B have originally, this is the quantum prediction, 1, 0 over root 2, right? This is the state that they originally prepared. And what I'm going to claim is, if I now, and I'm going to have to skip the algebra in this case, let A1 be now not the color of the particle, but I'm going to choose that A1 is the measurement of the Z1 operator, and A2 is the measurement of the X1 operator. So Alice measures either Z or X, and Bob measures a combination of Z and X, which is in this form. Okay. Okay, so he measures these two variables. V1 equals minus Z2 minus X2 over 2 root 2, and V2 equals Z2 minus X2 over. Okay, so there's a bunch of algebra which you can easily carry out because Z1 and X1 and Z2 and X2 are just matrices, and you're applying them to this entangled state and carrying out the expectation value without much more. I'll just give you the results. So A1, B1 is just this measurement. Turns out to be, let's see, B1 equal to 1 over root 2. A2, B1 will be 1 over root 2. A2, B2 will also be 1 over root 2, and A1, B2 will turn out to be minus 1 over root 2. So just matrix multiplication, carrying out you can think of these as the row and column vectors if you like, and then carry out the matrix multiplications and you get the answer. And if you sum up all of these now, so A1, B1 plus A2, B1 plus A2, B2 minus A1, B2 will be equal to 2 times square root of 2, which is always greater than 2. Okay, so that's the contradiction with the result that we got from the classical expectation value for this hidden variable theory. So this is the contradiction, or this is the proof. This is the CH-SH inequality. Okay, so if you prepare some entangled state, we evaluate this particular combination of A1 of operators or observables on the entangled state. Then, if it's truly entangled, it should give you this result 2 root 2. But any local hidden variable theory must be restricted to be below 2. Right, I mean it's lesser than plus or minus 2, of course minus 2 is already lesser than 2, right? So we can even drop the minus sign and say, just it's lesser than plus 2, okay? Right. So, yes?
So how do you define, why you want to define B1 and B2 like in this?
Oh, I didn't tell you how I came up with this. I'm just telling you that this is what CH-SH came up with.
Oh.
Okay, they came up, and this is why I want to tell you a different way to approach this entire inequality, because this doesn't seem very helpful, right? Physical, so to speak. Yeah, it's beautiful. It's obviously a mathematical theorem, so you can't dispute it, but it doesn't give you much insight into why, particularly that particular result, should be correct. Or how to choose different values or something like that, right? So we want to definitely examine this in greater detail, but I want to present to you the classic proof. The mathematical theorem is right here, and if you look in papers and stuff like that, they will always be referring to the CH-SH inequality, so I wanted you to see it once. So yes, so this is the inequality. So in the ultimate case, you should be able to violate CH-SH inequality by this factor 2 root 2, right, which is 2 times 1.414, so that's quite a large deviation, 2.8 approximately, whereas the classic prediction is less than 2. So there's a big gap between these two predictions. Okay, so that's just a mathematical theorem. I'm not saying that it's very physically motivated, but let me finish the conclusion and also say a little bit about experiments, right? So we should just finish this statement. And as you can see, it's a very simple proof in some sense. Of course, the big trick is how to get those particular, values. That's why, it's a famous paper. So the conclusion then of this theorem is, what have we assumed in the proof? Okay, we assumed what we call realism. Okay, that is the properties, which is what we normally think, right? So suppose we tossed a coin, right, and we got a result heads. We know the coin was capable of giving the result tails. In our mind, it's just like, oh well, yeah, when I measure the property A1, which as I told you was the position of the particle, let's say, it could have been in state 1 or state 2. You say, well, I measured state 1, but of course the particle could have been in state 2. That's how our minds think. This is the so-called counterfactual, as it is called. Meaning, whenever we have a result where things could have gone one way, our mind automatically thinks, well, what if results had gone the other way? Right? And we assume that the experiment or the measurement could have given the other result if we had chosen to measure it. That's always how we think, right? It's actually built into our evolutionary way of thinking, which is, how do you figure out how to go around in the world? You always think to yourself, well, if I do this, I could have gone that way, but if I had done this instead, I would have gone this way, and both possibilities existed. And for most classical examples, it is certainly true that this is possible, right? So this is what we call realism. The properties A1, A2, B1, B2 have values independent of observation. Because remember when I told you, when I gave that whole argument about the classical example, I said A1 minus A2 could be either plus or minus 2 or B1 minus B2 could be 0, and these are all the possibilities, we have enumerated them, so there's no way to violate this, right? Classically. And this is the property which is called realism. Okay? Something is there even if you don't measure it. That's the basic simple way to explain it. Okay? The other one is, of course, that Alice performing measurements does not affect Bob's measurement. This is called locality. Okay? And so, what we have shown by the proof of this theorem is that local realism, these two assumptions are indicated as one sort of theory. Local realism and quantum mechanics they contradict each other, right? They cannot exist simultaneously in this world. Okay? And so the question, of course, is now experiments, right? Which one is true? Right? And by now you all know the story. That in fact, people have verified the Chsh inequality many times. Okay? And it is then, therefore, if you believe then that the predictions of quantum mechanics, and which have been verified by experiments, we must abandon these two principles. Now it's a choice which one you choose to abandon. Okay? Because the local realism or these local hidden variables, they're composed of these two aspects. One is the realism or the hidden variables that Einstein was so fond of, and also later on, like Bohm, David Bohm, who was another famous physicist, he also came up with a lot of beautiful theories. or you must abandon the locality principle. Okay? And it's up to you which one you choose to abandon. Most people have abandoned realism. Okay? And because they want to stick to localism, which means that whatever Alice does cannot instantaneously affect what is going on in Bob's world. Okay? But maybe you are of the type who says, no, I would rather stick to this because this is more, what I want to believe in. That measurements could have gone the other way. That seems obvious, and we must stick to that. Then you unfortunately are in the position that you have to abandon localism, meaning you cannot assume anymore that signals propagate or information from one place to another can propagate faster than the speed of light, right? That's what this part of the thing says. Okay, so this is fairly huge, right? I mean, it changes your entire sort of philosophy of the world. So it's important to know that what the experiments have done so far, because we are claiming to abandon these two beautiful philosophical, or whatever you want to call it, obvious ways of thinking about the world based on these predictions of quantum mechanics that people have supposedly verified. So I won't go into, obviously there have been many sets of experiments now that have been carried out. So I'll just say the original experiments were carried out by Alain Aspect, and in the 1980s, and then his student Grangier, also in the late 80s, early 90s. So if you want, I'm glad to give you more references to these early papers that were carried out in the 80s and 90s, and to just give a general description of the experiments, what they did was they prepared atoms in a state which is what we call the Cascade Process. And so there's an atom which is a 3-level atom which has 1, 2, and 3. And what they did was, if you prepare the atom in this state, then it has a tendency to emit 2 photons. Okay? And the 2 photons are by definition entangled with each other because of the atomic interaction. That is, they have certain polarization properties that are defined by these atomic transitions. Okay, and then they took these 2 photons, Aspect did back then, he took those 2 photons into different, there's a possibility to separate them and then to do the measurements on these photons. Okay, and obviously you can imagine this was a sort of a very slow and difficult experiment to carry out, especially with the technology back then. They didn't even really have good computers or anything, so this is all quite a difficult but a heroic experiment, and he proved that in fact that these the Chsh inequality is indeed violated by these experiments. But there were questions that people had. One, he didn't really keep the localism property because he had a finite lab space. This is basically a table, right, with 2 things that were separated by on the order of a few meters. And so it was very possible, and his electronics was slow, so it was very possible that by the time he rotated, remember in the measurements that I told you, Alice had to measure, say, Z1 and X1, and Bob had to measure, say, Z2 minus X2 or something like this. So you have to rotate some polarizers and so on to obtain those measurements. So it's possible that somehow Alice rotating her polarizer could have affected the Bob's measurement result by propagation of the signal. Okay. Plus the other problem was that, okay, so let me not go too much into detail. Grangier followed up in the late 80s and 90s by using the so-called spontaneous parametric down conversion sources. Okay, so what he showed was that instead of using, and there are many people, okay, Zeilinger is obviously a famous person, GM Lebam, these all followed very shortly these experiments, and they did some really amazing and beautiful experiments, quantum teleportation, etc., that in the 90s, which outlined a lot of these same principles. But to be specific, Grangier followed up with these SPDC sources and showed that in fact you could start doing things much better, higher quality. You could verify these CHSH inequalities with much better results. But there were still a couple of loopholes in their experiments. These are the so-called detection and localism loopholes. Okay? These loopholes were never really fully closed. And the idea of detection, which is that because of the sources, these are the spontaneous parametric down conversion sources, they are probabilistic. Okay, meaning the essential idea is similar to the atoms. Basically, you pump a laser beam into a crystal, and the laser beam will occasionally, a very, very tiny fraction of the time, okay, if it's at frequency omega, will emit 2 photons at half the frequency. Okay, so these 2 photons very, very occasionally, right? Because it's a non-linear mixing process, so it's very weak in these optical crystals, but it does happen. Okay, and these 2 photons are therefore, by definition, again entangled with each other because they came from some initial, photon that had a certain momentum and polarization and so on. So these 2 output photons are now, of course, they come out probabilistically, and the experiments were only carried out when they knew that they had these 2 photons in the experiment. Okay, and you could argue, well, maybe there were some situations where these photons were not emitted, and the hidden variable guys, they just messed with your experiments in such a way to make it look like everything was, So this is the detection loophole, because you got a probabilistic or post-selected set of events. You only choose the events where you got a success to run the experiment, and people argued, well, that's not correct. You should take the entire set of events into place, not just the ones where you succeeded. And the other one is the localism, which is again straightforward. In spite of everything, they hadn't completely closed the loophole that things were happening on a sort of time scale that light could not have propagated and fixed the measurements, affected the measurement. So in in just this decade, there were a set of experiments in 2015. One is by Hansen group at Delft, and they used NV centers. Okay. And the other is Christer Schaub at NIST. Okay, and they used, and also Zeilinger in Vienna. These guys used again photons, except now with the availability of much better detectors, which are the superconducting nanowire detectors, plus the availability of very high quality entangled parametric down conversion sources, which are occurring at a much higher rate. They were able to close both the detection and localism loopholes even with photons. And the NV center experiment, what they did was, they took 2 NV centers and they caused the 2 NV centers to emit photons that are entangled with the NV centers. And then by a process which is called a joint Bell measurement on the photons, they took the photons and put them on a beam splitter. They carried out what we call the Hanbury-Brown twist of this joint Bell measurement on the 2 photons, and in that way they projected the NV centers into an entangled state. So again, it's probabilistic, but once the 2 photons are detected in a certain way, in a coincident way or non-coincident way, they know that the NV centers are now left behind in an entangled state. So now, conditioned on the measurement of 2 photons in a certain way, they are left behind with NV centers which are definitely entangled. Now they can carry out the same CHSH measurements that I just described to you, but starting with the knowledge that these NV centers are definitely entangled to begin with, and now we are not post-selecting. We are only post-selecting on those events where we detect photons, but when we do, we know that the NV centers are definitely entangled. Okay? And therefore, they were able to close this detection loophole, and they also separated these 2 cryostats, where the NV centers are sitting, by a few kilometers, 1.5 kilometers, almost a mile, 1.5 kilometers, and in that way, and because NV centers are solid state, they are able to do the measurements quite fast compared to atoms and things like that. They were able to carry out these measurements in such a way as to close the localism loophole as well. Okay, and so these are some beautiful experiments. Just happened literally a few years ago. As you can see, it took that long since originally in 1964 that Bell came out with his Bell inequalities. Okay? And I should also mention one more result by Weinfurter, Harald Weinfurter in Munich. And his group carried out the same results similar to the Hansen group, but with trapped rubidium atoms. So very similar idea, except now instead of using NV centers as the qubit, they used rubidium atoms as the matter qubit. So you can see that all of these things we are reading about in quantum information, and even things from like 60, 70 years ago, 1960s, are not necessarily all completely understood experimentally, have not all been verified experimentally, and suddenly we are still trying to understand a lot of things about this entanglement itself that we have not yet understood completely, even though these things, these concepts and these ideas have been around for, as I said, over almost a century since the EPR original paper came out. So what do I want to tell you today about, besides this CSSH inequality, is going back to Pinley's question about, how did they come up with these weird, basis states, and I mean, come on, it seems very weird. So I tell you in a different way, which I call the CHSH game, or the Bell game, or whatever you want to call it. Okay. This is a CHSH game. Okay, so we're going to put it into the context of like a quantum game. Actually, I should tell you that quantum games by themselves are an active branch of quantum information theory, because people are always curious about what things quantum information can give you that maybe classical information could not, and it was well known even before quantum information came along that thinking about games between people, where games are based on the information that each person has, is a useful way to think about what you can do in a classical information setting, and so they have also adapted it to the quantum information setting. So the kind of model that I have in mind is that again, A and B are sharing some entangled pair, and they participate in this game, and for this game I'm choosing that the state is just a little easier to verify, slightly different from the one that I just wrote down, the other EPR pair. I'm going to choose the symmetric EPR pair, 0, 0 plus 1, 1 over root 2. Okay? And the game is as follows. Let's say that initially Alice and Bob met together. Given this sort of my favorite joke in the past, Alice and Bob were grad students here at Pitt, and they went through their joint PhD program, and they were very happy. They made a nice entangled pair, and they took that entangled pair. One of them put them, they both put them in their fridges, dilution fridge, cryostat, or maybe by this point it can all fit in your pocket, in the future. So they have created this nice entangled pair, and now they're leaving, bye-bye, going off to exciting places, and they want to, in the future share information, let's say, right? I mean, and of course, I gave this example for the quantum teleportation experiment, but now we're going to put it as a game, and the game is as follows, right? Let's say that there are, they challenge people to participate in this game and claim that they can play this game better than anybody who does not have entangled states can play it, okay? And let's say that the game is as follows, that Alice, let's say, is sitting at her location, let's say it's on Earth, Bob is in his location, I don't know, somewhere else, across the galaxy, maybe in the solar system, and each of Alice and Bob, they also have nearby to them some neutral parties, neutral referees, if you like, okay, who can make sure that they don't cheat or do something bad during the whole game that they are carrying out. And the game that they say that they can succeed at better than anyone is that, let's say that the umpire tosses a coin, and the umpire A, right, tells Alice red or green. Okay? So they call out two colors. Okay? Just two colors. Yeah? And similarly, umpire B, calls out two other colors, pink, blue. Okay? And the choices are decided by these two umpires. Let's call them I don't know, C, Charlie, and P, David, okay, who are the umpires for A and B, and whenever they decide whether to call out red or green based on a flip of a coin, okay. So let's say that Charlie will call out red, and if he gets a heads in his coin, and green if he gets a tails. Similarly, David will call out pink if he gets a head, and tails if he gets a blue. Okay, it doesn't, or maybe I guess I chose heads. In my example, I better stick to what I wrote here. So, okay. So, and the game is as follows. If C, Charlie, says red, then A gives the result 0 or 1. They do something, they consult their secret, whatever list that they have prepared, and they give the result 0 or 1. And if C says green, then A gives the result again 0 or 1. Okay? Okay, I guess you can see where I'm going. Similarly, for Bob, if the umpire David says pink, let's say, then B. I wish I had colored chalk here to sort of make this a little bit more colorful, because I only have white, unfortunately. So B gives again 0 or 1 result, and if he says blue, then B gives again 0 or 1. Okay? That is, and now the claim that Alice and Bob are making to these umpires and to the whole world is, we can give you the following graph of results, okay, which I will just write as a graph, and I'll explain what it means in a second. Okay. Okay. So this is Alice. This is Bob. And their claim is that if I get a red on this side and a pink on that side, then my correlation will be perfect. Meaning, if I get a 0, Bob will always get a 0. If I get a 1, Bob will always get a 1. Okay? Similarly, on the green side, if I get a green and a pink, this correlation will be perfect. 0 will be exactly correlated with each other. A green, blue, the solid lines represent what I call correlation, and the dashed line represents anti-correlation. Meaning, if I get a 0, then, and I measure in the blue, or not measure in the blue, but you can see where this is going. If Bob gets the blue call, he will always measure a 1 when Alice gets a 0, and otherwise, if Alice gets a 1, Bob will always get a 0. Okay, so dashed line represents correlation, which is, for example, either 0, 0 or 1, 1, and the solid line represents correlation, and the dashed line represents anti-correlation. Which is 0, 1 or 1, 0. Okay? And there are other requirements which I have already outlined, which is that A and B cannot communicate once they are separated. Okay? No communication is allowed. In fact, we demand that they be so-called space-like separated, meaning once, say, Charlie throws the coin and obtains a head or a tails, and he gives that choice to Alice, within a few seconds, let's say, she must come up with the answer. Okay? She can't wait for a year and then give the answer, because maybe by that time the light would have had enough time to propagate to the other location where David is sitting, so then it's no longer a very fancy experiment or fancy game. Similarly, for David, once, and we can set up all these rules in advance, right? I mean, when they met on Earth, we agreed to all of, maybe everyone met first on Earth. Alice and Bob, and maybe Charlie David also went to grad school with them here in the physics department, so they make sure that everybody is being honest, or maybe they're chemistry people. Okay, so anyway, whatever. And so Alice and Bob cannot communicate, they're space-like separated, and Charlie and David, these guys, they're choosing the colors at random. They're not being secretly paid off by Alice and Bob to just give them exactly the colors that they want. Okay? Okay, so the claim that I make here is with any deterministic strategy or with shared randomness strategy, and I'll explain what these mean in just a second. A and B will succeed in this game only 75% of the time. And I claim with quantum entanglement will succeed in this game about 85% of the time. Okay? So again, this is in that same model that I had for you before of like letting Alice and Bob have almost access to almost any kind of strategy as long as it's classical. Okay? Meaning, as I said, when they first met up on Earth, they could have agreed to a strategy. Okay? And maybe the strategy was, hey, you know what? If you get red, always call out a 0. And if I get pink, I'll always call out a 0. And similarly, you can set up this graph ahead. You know what the experiment is going to be. You know what the graph should look like. So maybe you agree already. So let's imagine the deterministic assignment, as I call it. Okay? So first, let's think about the deterministic strategy. And deterministic strategy is exactly what it sounds. Prior to the entire experiment or game starting, Alice and Bob pre-assign, say, to red. Alice said, I'll always give a 0. If I get a green, I'll also always give a 0. Okay? And if you get a blue, why don't you give out a 1? And if you get a pink, you can give out a 0. And you can see this will certainly satisfy the solid bond over there. It will satisfy the solid bond over here. It will satisfy the dashed bond over here, but will not satisfy this bond over here. Okay? So we will get success 3/4 of the time because the coins are tossed, right? So there is a possibility 1/4 that you might get this choice red and blue, and with this strategy of deterministic assignment, you will disagree. Okay? So 1/4 of the time you will fail at this game. Okay? And therefore, 3/4 of the time you will succeed. Okay? And you can even convince yourself there is no assignment of 0s and 1s that will ever allow you to succeed at this game better than this 3/4 of the time. And that's because of the nature of this graph, which is such that it's not possible to have complete agreement on every vertex of this graph with just a deterministic assignment of 0s and 1s. No matter how I permute the 0s and 1s and 0s, I'll always come back to this 3/4 success probability. Okay? Okay. Now I add the shared randomness that I was telling you about. Okay, what is this shared randomness? It's just that maybe prior to leaving the planet, Bob and Alice, when they met up, they tossed some coins, and these coins were tossed let's say they toss, I don't know, 10 coins or something, you know, or maybe what did I choose? 4 coins, okay? Alice and Bob flip a set of 4 coins because there are 4 possible, you know, sort of basis choices. So they choose 4 possible coins, okay? They flip 4 coins. This is the shared randomness strategy, okay? And they get some result. Okay, they toss it once, they get a result, and they write down the answers, H, T, T, H, let's say, was the outcome of their coins, okay? And what is the idea is, of course, because this is just written on a piece of paper, they can just make a copy of this piece of paper, and each one takes a copy and goes to their respective planets or whatever. And now the agreement also is that if Alice, and I'm going to write that as a function now, function that if Alice is given the choice read by the umpire, and she looks at her choice of coins, okay, looks at her shared coins, she's going to give 0 or 1 based on this set of coins, okay, and then you know she can choose whatever she wants. Like, I mean, she might say, well, if the outcomes, if my coins are HTTH and I get the choice red, I will give 0. And if the outcome is, and if the choice of basis is now pink, let's say, some function of this, whatever, you can construct some circuit fancy that you like, whatever, that takes this randomness as an input, takes the basis choice as another input, and spits out a 0 or 1. So she has a little classical computer or whatever that allows her to work with this probabilistic choice, and she just gets this result. Well, of course, this function, right, this computer, whatever it is, in the end must output some values of 1s and 0s. Let's say in particular, I'll just use this since I already wrote it down. Let's say in particular it puts out, say, 1, 1, 0, 1. Okay? Then, again, you see that this has succeeded 3/4 of the time. It has worked on this basis, it has worked on this basis, it has worked on this basis, and has not worked on this basis once again. I guess I have some prejudice. I made only this bond fail every time, but you can make any other bond fail if you like. Okay? And again, the conditional success probability which is probability of success given some inputs H, T, T, H, okay, is 3/4 once again, as you see over here, right? I succeeded 3/4 of the time, and now the probability of success overall is simply the sum over all the possible configurations of those coins that I initially started with. So the probability of success that is not conditioned on the configuration, simply the sum over all configurations times probability of success given the configuration times the probability of that configuration. The probability of success given a configuration is always 3/4, so I can take it out. 3/4 times probability of configuration, and this, of course, the sum over all these probabilities is 1, so this is again 3/4. Okay, so we have again shown that either using shared randomness or the deterministic strategies, that this game can never work better than 3/4 of the time. Okay, and also there's one more strategy which you could call private randomness. What is private randomness? It means that Alice and Bob, they didn't share a set of these coins. They each had their own individual secret coin that they constructed. Okay, and when they, which the umpires and all cannot see, they just look at their private key, private random number, and whatever the result of that random number is, they will produce the output 0 or 1 once again. You can easily show, or you can see already that private randomness is nothing like having one more secret coin over here, call it, one more coin that, that Alice kept with her but did not share, and they didn't use that result when they flipped all the coins on her. They just kept it secretly, didn't tell the other person, and kept it for themselves. Once again, the same argument for this probability of success given configuration and probability of configurations will give you the same answer 3/4. Okay, now we come to the quantum entanglement, and this is where Pindlay's question about how did they select those bases will hopefully become a little clearer. I realize also the inequality here is 3/4 rather than 2, but that just came from in the CHSH inequality they assigned the values +1, -1, and here we have assigned the result 0 or 1. So by rescaling the entire outcomes of all the results from the CHSH inequality to, instead of being between ±2, now it can only be ±1, you'll easily show that basically the same outcome is satisfied. Okay? The same inequality is satisfied in that situation. Maybe you can do that as an exercise. Okay. So now we come to the quantum entanglement case. What do these various choice of colors mean? Okay. Well, for that, we will just go to our block sphere, or in this case, even forget about block sphere, we're just going to look at the equator of the block sphere. Okay. And the basis states that I'm going to choose, well, the obvious basis state is of course this basis state, 0 or 1, right? Okay, so this is, let's call it the red basis. Okay, so Alice's red or basis is always 0, 1. Okay, remember that's the configuration over here: red, blue, pink, green. Okay, and let's say that pink. Well, okay. Before I go on, let's say pink for a minute, because you can see that pink needs to agree with red most of the time, right? Pink and red need to agree most of the time. So Bob maybe should choose a basis that is close to 0 or 1, 0 and 1, but maybe slightly rotated. As an example, he chooses a rotation on the order of pi/8. The reason for pi/8 is this is a famous gate in quantum computing, so I just chose that. So this is pink basis, okay, which is cos pi/8 sin pi/8 will be the 0 state in that basis, and the 1 state in that basis will of course be minus sine and plus cosine. Just rotation in that, in this, so this is pink 0 and this is pink 1. Okay? And then you can ask, what about green? Well, clearly proceeding in the same way. This should be again rotated by pi/8. Okay. This is green 0 and green 1. Now what about blue? Well, you see that blue is the one that needs to be almost anti-correlated to red, right? So what we should do is we should have the blue 0 be very close to the 1 of the red state. So this is the blue. So blue 0 and red 1 are very close to each other. Okay? And of course then there is another 90-degree rotation, which is okay. This is blue 1. Okay? So these are the basis states. I won't write them out explicitly. Hopefully the diagram convinces you. Each one is just rotated by pi/8 for their individual states. Okay? Okay, now we can ask, what is the probability that if Alice measures in red Okay? So pink 0 and red 0 are very close to each other. So probability that Alice gets a red equal to 0 and Bob gets a pink equal to 0. What is this? Right? Well, if Alice got a red going to 0, and we know that Bob should also get a 0 in the original entangled state. Remember the original entangled state that they shared? Psi equals 0, 0 plus 1, 1 divided by root 2. So if Alice gets a 0, Bob must have gotten a 0 also in that basis, but he has measured in the pink basis, which is rotated by pi over 8, which means there's a probability cos squared pi over 8 that he actually gets the 0 value. Right? Okay? So what is this? This is cos squared 22.5 degrees, which is 1/2 plus 1 divided by 2 root 2. Okay? Similarly, you can show all the other situations. I just erased the correlation. Anyway. You can, and by the way, this value here is 85%. Okay? So if Alice again measures red 0 and Bob now measures in the blue basis and wants a blue equal to, let's say 1, you can easily show the probability that Alice gets a 0, which means that Bob must have also got a 0, but now 0 and blue are separated by this much. Okay? So, in fact, this again will turn out to be the same as 1 minus the probability that Alice got a 0 and Bob got a 0. And this is again 1 minus 1/2 minus 1 over root 2, which is again 1 plus 1/2 plus 1 over root 2, which is again 85% approximately. Okay. So again, remember, I erased the board, the correlation function or the correlation game that I want to play, which is that Alice and Bob want to have correlations, exact correlation, if they were measuring in the red and pink basis, and they want to have anti-correlation if they were measuring in the red or blue basis. You can also carry out the same argument for the green and red and so on, and you see that the quantum entanglement will succeed with a probability of 85%. Okay. Okay. So the statement that that the probability will always be lesser than or equal to 75%, which is the classical or local realistic picture of what will happen, is called the Bell's inequality, which is now also referred to sometimes as the CHSH inequality because of the more general proof that was provided by CHSH. And this whole game was just a way of explaining to you how we could use this Bell's inequality or this CHSH inequality as a way to sort of understand the choice. So if you go back, you can show that the choice of these bases is equivalent to those measurements that we made in that CHSH inequality. Okay. I hope I convinced you. So what do I want to finish up with? So the last part of this statement of this game, I want to just briefly tell you about two other kinds of paradoxes or inequalities that are very famous in quantum mechanics. I won't have time to go through all the math of these claims, but again I want to just leave you behind with a sort of, why it's so weird. Okay, one is called the G and Z state. How much time do I have? Okay, I basically have 1 minute. Maybe I'll take 5 minutes more, just to give you sort of an outline of these things. Okay, and the further reading again you can refer to Mermin or Nielsen and Chuang. So they consider the GHZ state, which is the following, which is a 3-qubit state. Okay. If you look at this state, which is the 3-qubit state, psi, then you can see that the outcomes of measurement of, let's call this the bit 0, the least significant bit, this is the next highest bit, and this is the bit 2, right? So there are 3 qubits, least significant, the next from that, and the most significant, 0, 1, 2. You can look at the output of these measurements, right? And you can verify that this equation must hold. That's true because either all the bits are 0 or at least 2 of the bits are 1, right? And therefore, if at least 2 of the bits are 1, their addition will give me 0, and the third bit will be automatically 0 in that case, and therefore the output is always 0 modulo 2. Now, let us say that, instead of measuring in the logical basis, I have a choice of applying Hadamard's first to say qubits 1 and 2. So that is, I choose first to apply H2, H1 on psi and then measure. You can see where this is going. Now I want to prove the algebra here. I'm just going to write the answer that H2, H1 applied on the state psi, okay? H2, H1 applying on the state psi will transform the state such that now it satisfies the following equation. That is the second qubit with the Hadamard applied plus the first qubit with the Hadamard applied plus the X naught must be now 1. Okay? And the reason for this is that the H2 and H1 basically change the parity of these states in such a way that at least either one of the qubits has got a 1 in it, or all 3 qubits are in the state 1. Okay? So it's the opposite of this, where at least 2 of the qubits were 1, now only 1 or 3. It's like either 1 or 3 will be in the state 1. Okay? So the two Hadamards basically change this output measurement. Okay? Now so again we come back to this idea that these Hadamards could be chosen to be applied randomly or not chosen based on flips of some coin. Okay? So let's think about that for just a second, right? At first you say, well, either the Hadamards were applied or they were not applied. Okay? So you can't really compare the value of X naught that you get in this measurement versus that measurement, right? Because after all, this X naught will give me this result, okay, that is that X2 plus X1 plus X0 equals 0, right? That will be true if I don't apply Hadamards, and otherwise this result will be 1 if I apply the Hadamards, okay? And the idea is, can we compare those two values of X naught? So as I said, it seems silly. These are mutually exclusive events, right? The mutually exclusive is either I apply Hadamards or I don't apply Hadamards. But suppose we do something different. We measure first, okay? So this is case 2, this was case 1. And now this is case 3 or star, whatever you want to call it. Measure first qubits 1 and 2 and then qubit 0. Okay? Okay? So if no Hadamards were applied from this equation, we know that x0 must be equal to x1 plus x2. Which means that by measuring the outputs of 2 and 1 without applying Hadamards, the value of x0 is determined completely, right? It doesn't matter what I do to x0 after that. I could choose not to measure it. And I would know, according to our classical way of thinking again, that x0 must be 0. Obviously, right? I mean, I measured 1 and 2, I got their output result, then whatever that output result is what x0 must be according to this simple relationship. So the outcome of qubit 0 is predetermined by the outcome of the earlier measurements 2 and 1. Okay? Now here's the key point. Since qubits did not interact after we prepared, once again I'm using that same analogy that I separated all the qubits, they're far away from each other. We never have to interact them again. We just carry out Hadamard's or not and then measure them, or we don't carry out Hadamard's and measure them. Okay? So the qubits don't interact before, after the preparation. It seems like no matter what I did to the bits 2 and 1, I would always get the result x0. The x0 will be predetermined by this equation, which is, call it star or something like that. Okay? So even before 2 and 1 were measured, the output star is guaranteed according to the preparation step of the state, which means, remember, 1 and 2 are now far away separated. They cannot possibly interact with the original state of qubit 0. So why don't I apply the Hadamard's to 1 and 2? It doesn't affect the result of x0. x0 is already determined by this equation. Okay? So why not apply Hadamard's? So therefore it seems like the value of x0, whether I apply Hadamard's or if, remember this was the equation 2, okay, and that was the equation 1. Whether or not I apply the Hadamard's in 1 and 2 equations should not affect the value of x0. Which means what I earlier said were two exclusive possibilities. Either I apply Hadamard's, don't apply Hadamard's. These values of x0 should not depend on that particular choice of whether I choose to apply or not. And because the qubits 0, 1, 2 are all equivalent, as you can show, their permutations, permuting the qubit 0, 1, 2 in that state doesn't affect the output or the state of the system. We can similarly carry out the same equations, which is x2h plus x1 plus x0h is equal to 1. x2h plus x1h, x2 plus x1h plus x0h is equal to 1. So we have now equations 3 and 4 as well. And we can apply the same arguments not only to x0, okay, where we decided to choose to apply Hadamard's to x2 and x1. I can also apply the arguments to x1, whether I choose to apply Hadamard's to x2 and x0. Same thing with x2, whether I choose to apply Hadamard's to x1h and x0h. I can also go the other way. Imagine that x0h, x1h and x2h were the original states, and whether or not I choose to apply the qubits, the Hadamard's to them. By this reasoning, we see that all the values, if I add together all these values, okay, I must get, because 1 appears in the right hand side of these equations, okay, so I add together LHAs of all these equations. Each of these values, x1, x2, x0, all appear twice in these equations. Same with the x1h, x2h, x0h. They also appear twice in all the equations. Therefore, adding them all up together, because when two quantities are added together which are the same, modulo 2, then they give you 0. So the adding together the LHS of all the equations, you get a 0. But adding together the RHS of all these equations, 1, 2 of all equations, 1 to 4, leaving out star. Star is just a result to show you that the value of the 0 qubit must be determined whether or not I apply Hadamard's to the other qubit, in this classical way of thinking. Okay? And what I'm saying now is, on the right hand side, on 1 through 4, I have 0, 1, 1, 1. So 1 appears odd number of times, which means the answer must be 1. So I've just shown that 0 equals 1 in this classical way of thinking. Okay, and so this is a even deeper paradox, if you like, compared to the CHSH inequality, because that's just an inequality. Here I've shown an actual equality between 0 and 1, which comes about if I continue to insist that x0, x1, x2, these outputs of the state of measurement exist whether or not I choose to measure. That is a key point. Again, the realism, remember, that I introduced to you, which is that the output values are independent, or they could have had those values whether or not I chose to measure them. That realism has led us into this trouble that, that this now 0 must be equal to 1. Okay? And therefore people abandon either realism or localism again, because otherwise we will end up with paradoxes like 0 equal to 1. There's another famous paradox which is called the Hardy paradox, okay? And where he shows a very similar idea, not with 3 qubits but even with 2 qubits. He just uses a different state. Okay, so we have been using the Bell state, or now the GHZ state, but he uses a different state which is called the Hardy state, with a Hardy entangled state, and that entangled state for 2 qubits is already enough also to give a very similar type of paradox. Okay, and you can read more about that, or I can assign it to you in the notes how to think about that paradox as well. Okay, so that concludes basically our entire course. I hope you have enjoyed these sort of lectures on quantum optics and quantum computations. As I said, next week we will have the presentations, Tuesday and Thursday. I haven't found the room yet, but as soon as I do, as soon as I get the information from Michelle, I'll email you guys so that you have the room numbers. Okay, see you next week.